Awesome. It looks like we are live and broadcasting.
Yeah, we are.
So at the very beginning, let me use all the languages that I'm capable of using to say hi. So hi, cześć, привет, hello, oi, salut,
Hola.
hola. If you are hearing us and seeing us, please just write a comment so that we are aware that you are there and listening. And we'll be starting this show within like a few seconds right now. Just if we see any comments, I can see that there are some people already. If you could comment that you are there and listening, that would be great. Just the first person to see. Let me post it.
Nobody.
Okay, I can see that we have 17 people in there. So let's start with webinar. Welcome. Today webinar is hi, ahoy, hola, hello, welcome everyone. Today's webinar is related to async expert and will be hosted by 2 out of 3 Dotnetos. So it's me, Szymon Kulec, nickname is Kulec, and
me, Łukasz Pyrzyk. Hello, everyone.
Awesome. And this webinar will be solely focused on counting and average. And we'll take a look at average from various points of view, and we'll hopefully make it really fast and really, really efficient. So let's move on with counting and average. As I mentioned, it will be about different approaches to counting this specific value, but we want to warn you though. First warning is that we do not encourage using averages as statistical value. On average, it's just a waste of time. And please use something meaningful, something like mean, median, percentiles, and libraries that support that. For instance, for benchmarking, you can use the mighty, the awesome benchmark.net. The second thing is that we'll try to show you some low-level stuff that is needed for writing an efficient async-ready code. And async-ready or async-aware, anything that is async-related underneath will probably use the methods or classes, APIs that we'll present during this call. The last but not least, if you feel any dizziness or take a dislike to logging or writing awful code, please contact the closest async expert or become one. So without further ado,
Yeah, so we are supposed to talk about average, but you mentioned that average is not the best option for us. So can you tell us why the average is so terrible?
Yeah, so whenever someone mentions average, it reminds me of this terrible statistical dead joke that on average a person and their dog have 3 legs. And on the other hand, the average from our point of view is quite interesting because it requires counting and summing some things at the same time. So it's not that like you just bump up one value, but you need to work with 2 values at least. The third point is that it's funny to play if you want to use a few concurrent agents. By agents, I mean either threads, tasks, workers, whatever, a few concurrent entities working on this single element. So yeah, let's assume that we will count an average value of something. We'll try to do it in an efficient manner. And at the very beginning, we will start with a single thread task for it. How about it, Łukasz?
Yeah, it should be quite easy. So maybe we can jump into the demo.
Awesome. So yeah, take a look at the following snippet. It's a really simple implementation of average. We will just use two fields to make the calculation happen. The first is the sum that we will increment whenever something reports the value. And the second is the count that will be incremented by 1. So basically, whenever a value is reported, we will increment the sum by the value and increment the count by 1. Having this said, if we take a look how the average property would be implemented, we would just divide sum by count. And again, just for brevity and to make this sample short, we will make this assumption that the count is greater than 0. So basically that someone or something reported at least one value before accessing the average. And as we can see in here, it uses only two fields, the sum and the count. It works and it calculates the average whenever that's needed. I mean, whenever you access the average property, it will calculate the value over and over again. So yeah, just to try to, if we wanted to try and to come up with a benchmark or a load test, if you would like to call it this way, that would be the following one. So we would just instantiate the simple average, and then within the outer loop, we would try to mimic multiple workers. I mean, yes, that's a single threaded code, but we want to make it look like there are multiple workers, multiple threads, tasks that try to do the counting. The inner loop would basically spin from 0 to size. As you can see, the size is 1 million. So we can assume that the average.report will be called 4 million times. Is it okay to use that?
It makes sense.
Like that? Yeah, so just to get some really raw basic number that we will later use for some comparisons. So if we run it, we will see that it will take around 7 milliseconds to run it, and that the standard deviation is 0.3 and the rest of the number. And that's just like a really basic raw number that we will use for comparisons. So yeah.
We simulated the single-threaded application with multiple workers, but can you provide some kind of algorithm or maybe the approach how we can handle it when we want to parallel the work and separate each thread, for example, to upgrade its own counter, or for example, to upgrade the shared counter? Do you have some ideas how we can do this?
Sure, definitely. Probably the very first answer, as always, is to use not so mighty log statement. So so what we can do in here to make it multi-threaded ready or thread safe, we could introduce a single field that would store the sync object that we would log onto, and then we would update the report method with the log statement. So basically, we would add the log around the sync, and then both sum and the count would be incremented under the same log in an atomic fashion. To make it fast or to make it short, maybe, we would also add the average and log in the very same manner. So basically, just add the log statement in every method, log on the same object, and then we are sure that basically no two operations can be run at the same time. And at the same time, the average will be reported properly, meaning that it will take into consideration all the values that were written till this specific moment. So, and just to compare that with the previous benchmark or previous load test, if we want to call it this way, we'll assume again the worker count for the size is 1 million. As you can see, we instantiate the average at the very beginning, then we spin multiple threads. We pass the value in there, and then we just report the value. At the very end, we use the start API to start all the threads, and then we use the join API to wait until the computation is finished. I mean, there is nothing fancy in that, and we don't want to dive into like the thread API. Just this is presented as probably the simplest idea of running a benchmark like this against a specific leverage.
My quick assumption. So now we have 4 workers. So should it be 4 times faster?
Yeah, let's take a look at the table. So as we can see, it's really terrible in being fast.
So it's 32 times slower, where I thought it would be 4 times faster.
Nope, it's really terrible. And again, I would like you to remember this number as a rough estimation, something that we will work with. It's not like this is the benchmark. This is just a rough basic number that we'll try to improve.
Okay, but I bet we can do better.
Oh yeah, I mean, you just won the bet probably. So let's move on to something else. And by something else, what we could try to use is the mighty interlocked. So first observations. We are aware that lock wasn't performing that well. The second point to add is that the interlocked class. If you are not familiar with the interlocked class, it provides a variety of highly effective atomic operations. For instance, in our case, these two will be quite useful. The first is interlocked add. The second is interlocked increment. So basically, you can atomically increment or add one value to another without using the previously not that well-performing log statement. Just a bit deeper dive into how it works underneath. If we take a look how it works on x86, x64, we would see that the the assembly that goes out of the JIT is prefixed with this log prefix. And what log prefix does actually, it takes log on an address, being more specific, a cache block or a cache line, when executing this read, modify, write operation. So we can think of it as let's start the log, then read the value, modify it either by adding the value or just incrementing it, and then writing it back, and then the log is released. So
okay, so we can move log from C# level back down to the assembly level, but there's still some kind of logging mechanism, so it won't be free. There is some kind of performance penalty on this log keyword on the assembly level, right?
Yeah, definitely. For basic atomic operations, you can definitely phrase it like this: we are pushing the log down to the assembly level, hoping that our approach will get us better results. The other part related to interlocked is related to volatile, and either you use volatile read or write. The semantics are related to the release acquire semantics, and just let's not dive into the really low level details in here, but the really rough description of it would be that volatile ensures some kind of ordering of operations. So if you have multiple operations and you imagine that you've got C#, then it's jitter, then it's assembly being executed on your CPU, there are many operations and many optimizations that can be applied to make it run faster. So volatile read and write basically applies some barriers and disables some of these optimizations, ensuring kind of ordering of all the optimizations. So it's nothing related to...
Shimon.
Yeah.
Because I remember in my first project in my whole career, I noticed the volatile keyword next to a field in my class. Is it the same volatile here that you mentioned, that volatile read is the same?
Yeah, that's a very good question. So the semantics behind volatile as the keyword that you can use to prefix field in C# and volatile class is very same. So it's basically acquire release semantics. The big difference And hopefully we will see that we will leverage that at the very end of our journey, is that with volatile field, any read or write to this field that you would just write in your C# code would be volatile. So it would issue these barriers and disable some kind of optimizations. If you are familiar enough with your code and you know what you are doing, you can use volatile read and write, meaning using volatile class, to apply the acquire release barrier semantics only to specific areas of your code. So you don't have to make all the reads or all the writes volatile, but you can just choose them, but you need to choose them wisely. So that's basically the difference. But yes, the semantics is the very same. So that's the acquire release semantics. But yeah, that's nothing related with caching in CPU. Just forget about the caching. It's only related to ordering of operations and preserving the memory model. So just to give you a brief look of the usage, if we had these two fields, field 1 and field 2, sorry for such a silly name, but that's the best that I could come up with. If we read the field number 1 in here with volatile, we are ensured, if the writes are done in a right manner, but let's assume that they are, we are ensured that the field number 2, the value read from them, will be no older than the value that was read from field number 1. So again, let's not dive into the into details, but you can see that there is some ordering and some preservation of the ordering of these operations.
Yeah,
yeah,
that's right.
Let's try it out. As you can see, and as you probably heard, the interlock provides us with two separate operations. We can't bump up a single number at the same time. So to report a value, we would use two different methods. The first, interlocked add, to add the value to accumulator. The second, which is count, we will just increment it as it was in the previous example. The average, we will use volatile read to read the count, but as we remember, with volatile read, we are not ensured that the sum will be read at the very same time. It can be something newer than the count. So that's why this example will be eventually consistent, meaning that if you are reading the average in a loop, eventually it will provide you with the right answer, but during the calculations, especially with the two interlocked that also are not executed atomically, you may run into a scenario where the return value is potentially incorrect for a short period of time.
Okay, but a quick question back in the previous slide. So I read the count with volatile, but I don't read the sum with volatile. Can you remind me once again why? Why I can read volatile only?
Definitely. So volatile read preserves sum of ordering. If the count was written with a proper barrier and interlocked add and increment, they issue this kind of barrier, we are ensured that the sum will provide you with a value that the read of the sum won't be optimized before the count. And that's the only behavior, that if you read the proper count, the sum might be only newer. So hopefully it will be from the same report.
Okay, thank you very much.
Let's move on. So if we take a look at the benchmark or load test that is almost the same as we saw before, we can see that this eventually consistent interlocked average, quite mouthful name, sorry for that, it takes 226 milliseconds. So it's all as terrible as the logged approach.
Exactly. And it's completely more difficult to understand, right? We added some kind of interlock, some kind of volatile read, but the benefit is nah.
Yeah, so probably we have option right now. It's either it's not spicy enough if I wanted to put it in Dotnetos terms. So we need to make it, we need to add some spice to that. So yeah, the basic observation is that it looks like the two atomic operations might not be better than a fast lock. Again, this is just rough estimations. Please don't treat it like the only result that you can obtain. We are just comparing some numbers and trying to squeeze the performance out of it. So yeah, probably.
Do you have an idea how to fix it?
Yeah, I mean, my guess would be that if we have two atomic operations, maybe we could get it with one, but how to make it? Okay, so observation so far, locking, it takes a while.
Yes.
Multiple interlocked instructions, even if they do not lock, actually, I mean, we don't have this monitor and lock statement in C#. It costs a lot. And we want to move towards less locking and less locking. We can say, but maybe our lock had a bad day or interlocked, but we can easily move forward and try to replace two operations with single one. And maybe we'll be able to keep the semantics at the same time, meaning that we can report values and take the average, and maybe the calculations will be even more accurate than before.
So is there any magic method that allows you to update two variables, for example, with atomic operation?
We can make the magic or make it work. So yeah, that's a very good question. So interlocked add has multiple overloads. The first that we used before is related to interlock.add, and basically we just pass a reference to an integer value. But there is also another one which uses long. So yeah, we have 2 bytes, or we had 2 integers, that each takes 4 bytes because there was the count and the sum.
Exactly, yeah.
2 int variables or fields can be encoded in a single long. I mean, we have 2 integers, 4 bytes long, so 2 times 4, that's 8. So hopefully we could pack it somehow into a single long value.
Of course, because long takes 8 bytes, right? So we can pack 2 ints into a single long variable.
That's correct. So that could be done with the like the old black magic from C++, where we can use the bit shifting operators. So in this case, as you can see here, we are moving the sum 32 bits to the left, and then we apply the bitwise OR operator, adding the count to the lower 32 bits.
And can you explain me quickly why 32?
Oh, yeah, sorry, I should have mentioned that. So 32 comes from every single integer, it's 4 bytes. Every byte is 8 bits. So 4 times 8 is 32. So that moves the sum to the upper part of
in that case, I want to shift enough just to have a space for another integer, let's say.
That's correct. That's correct. And that's the way how we will encode our value. And now just bear with me for a second. If that's the complex thing, just bear for one more second. And as you can see in here, we can take into consideration 2 values that are encoded in a very same way, that we move the sum 32 bits to the left, and then we OR it, bitwise OR, with the count. And what happens if we add 2 values that are encoded like this? We will add the counts, we will add the sums. So it looks that this operation is actually additive, so that it preserves the encoding, so that if we add this value one to another, we will be able to extract the real count and the real sum. Of course, we do not consider cases where number of counts is bigger than integer, or the number of included in the sum is bigger than integer. That's for small values, of course. But we can see that this operation preserves the encoding. So we could actually extract it. So yeah, let's try it out. What we will use in here is that we'll modify the report value to use a single interlocked add operation. As you can see in the report method, there is this shifting and ORing with count increment. And for average, we will read using the volatile read again to preserve that every read from the store is properly ordered with the rest. We will obtain the value, then decode it, divide it, and return it. So we basically cut the number of interlocked operations in half.
Makes sense. So from interlock.add and increment.increment, we have only interlock.add, but now we are operating on a long, and this long holds 2 integers. So we did a magic to have 2 values under the same field.
That's correct. We basically packed them up to store them in a single field and access it within a single interlocked operation. So if we take a look,
spicy.
Yeah, definitely. So if you take a look at the benchmark, it looks like it's almost 50% better. And as you can see, we can notice in here a huge drop in the time of this benchmark. So mean actually is now 116, and again, standard deviation is also halved, or even is probably even better. Yeah. So it looks nice. Quite nice, and we can ask, okay, can anything be done in here? Can we push it forward? And I would like to encourage you to revisit our assumptions. So assumptions were the following. There are some value reporters. You can think of it like, for instance, some components in your ASP.NET application, or something that you want to basically report and then take the average out of multiple reporters. There is a need to aggregate the average from time to time. And my assumption is that we want to make the writers really fast, but the aggregation, it should be fast, but it doesn't hurt if it's a bit slower, because you probably want to display it on in a kind of a dashboard or something. So we are fine with making the reader part a bit slower, and we strive and we are pushing to make the reporters much faster. And the last but not least, I mean, writers are separated from readers. So there are some components calling report, and there are some components trying to obtain the value. So the question is that, having this set and observing this kind of situation, can we make it a bit better? And maybe can we shift a bit of work from the writer to the reader?
If you ask this question, I think you may know the answer, and we can optimize it even more.
Yeah,
right?
Definitely. Let's make it even more spicy. So what if every single writer had its own thing to report to? So what if every single writer had only one thing that it works with, and it doesn't need to deal with all the friction with other workers? On the other end, so on the reader end, we would need to assume that we can visit all the different reporters and ask for this count and sum, and then aggregate it properly. And then let's assume that we are basically fine with making the readers heavier. So having this set, we could come up with the following one. We already have this packed interlocked average. that we can basically multiply or instantiate multiple times and just use it because we already have this implementation and we can move forward with that. So we will modify our test or benchmark or the load test, as I mentioned before, that just for sake of the test purposes. As you can see, I moved the line with the instantiating of the average inside of the loop. So in this case, every single thread will obtain its own average instance. I mean, if we wanted to make it available for the reader, we would need to store these instances somewhere, for instance, a list or an array, something that is later on accessible by the reader to access all the values and gather them and combine them properly. But for the sake of the writer benchmark or load test, we can just move it a few lines lower and it mostly should be fine. So if we take a look at it and run this simulation, we will see that we are way much better than before. So we dropped to 12 milliseconds.
Yeah, it's almost the performance of the algorithm, which is not thread safe, right? That is based on simple adding two variables.
Definitely. So we can see a huge improvement because what we did is from our observation that we can move the work to the aggregation phase and just leave every single writer or worker with its own average instance. We were able to split the write-heavy load from the potentially a bit heavier read part. So yeah, there is no contention from the reader taken into consideration in this sample, just to mention that. But as always, we could ask the favorite question, can we do better? I mean, it's...
I guess we can, right? Because I see your face. You have some idea.
Of course. I drank enough of our spicy sauce. So let's push it forward. Let's revisit again what interlocked add gives us. So the first thing is that it ensures atomic read, modify, write. So again, we can atomically obtain a value, modify it, and write it back. And it is useful for multiple writers. I mean, if you have multiple writers that want to act on a single value, that's the way you do it. But now we have a single writer. So yeah, so there are no multiple writers for every single count and sum that is stored somehow. So maybe,
you're right.
Maybe we could dump it all together. I mean, there is no use. We have a single writer. We have a reader that will go through all the components, but we have a single writer for every instance of this average. So how can we revisit it and move forward with the final optimization? So if we take a look, let's revisit the report method that we used. We have interlocked, add, store, and then, I mean, I just inlined all the constants in here. So we just do the bit shifting magic in here to use it in a single line with a single interlocked add operation. If we rewrote it to make it a bit more explicit, and if we had this atomic keyword in C#,
it would be great keyword.
Yeah, probably. And transaction memory and all that stuff. Yeah, but let's assume that we have this atomic. Okay. So the implementation would look like, first read the store to a current variable, then add to the current the value that we calculated above, and store it back to the store. And that's the atomic operation that we run with interlocked. That's the semantics behind the interlocked add.
Makes sense.
So again, let's take a look. Just store the value in the current, bump it up. But we have a single writer. So what we can do in here is that we know that we are the ones who write the value and read the value back. The only fact that we need to take into consideration is that the write that we do should be finally visible to the reader, meaning that it won't be optimized away in an infinite, I mean, being pushed or stored somewhere. We want it to be visible somehow.
Because we don't have parallel writers, so we don't care if they, let's say, compete for updating the value in the same time. We just want to make it available later, right?
That's right. And actually, we are the only owners and the only writers to the value. So we don't have to care about who stored the value in there anyway. So what we could do in here is that instead of doing it in an atomic way, we could just read the value, because that was the component that a task, a thread that actually wrote value in the store, and then use volatile write to properly set the value in there. Again, just to refresh what volatile write does, it will ensure that the values, there is some kind of ordering with the acquire semantics. Let's not dive into acquire semantics, but there is some kind of memory barrier that will prevent some optimizations. And this can be read as eventually the reader, if it uses volatile read, it will eventually read the value that was written by the reporter. So now we removed the aspect of interlock. We don't longer lock it. We no longer use this atomic operation, because we know that we are the only component that uses this instance of average. We just bump it up and use volatile write to write it back. And just for sake of reference, on x86, x64 architecture, all these volatiles will be highly likely evaporated during the whole compilation to assembly, because the model behind CPU, x86, x64, is really strong. For ARM, it won't be that case. Yeah, but it should be so much better anyway than using a fully atomic operation. So if we take a look at the benchmark, we will see that the reader-writer average takes 6 milliseconds.
So it is faster than the original approach, where we have no, let's say, thread safe, no approaches, simply incrementation of the variables, right?
That would be true, but we need to take into consideration that the first single average was looping, had this outer loop running 4 times. So actually, it's not that faster, because we had it was running 4 times to simulate kind of work, the kind of work that we want to use. But yes, it's pretty amazing. But the simple average was running it 4 times, so it's not that fast. But still, we halved it, and again, we are 2 times faster than the previous attempt. So again, the reader is not taken into consideration in this sample. And as I mentioned, the volatile read-write should have no visible penalty on x86, 64. It will be mostly evaporated during the compilation.
So we are saying that there is a huge amount of chances that this whole volatile thing would be optimized, that we will have no cost of having these volatile keywords at all?
Depending on the scenario, but the best answer will be yes. So for regular CPU, the consistency model, the memory model, is so strong that it preserves the majority of operations. So yeah,
very nice.
So yeah, that was our final attempt. I mean, we are really fast. We use this single writer principle. So now let's take a look a step back and let's revisit all the steps that we observed. So the first, our approach was the logged average. We just added the log to a single threaded or single threaded solution, and we were observing the performance nightmare. Sorry, that was the case, and that's the perfect name for it. Later on, we used two interlocked operations with the eventually consistent approach, where we basically lost the atomicity because of the two different operations running at the same time and reading count and sum using volatile read. So yeah. Packed interlocked average was about let's use the bitwise operations, so bit shifting, packing bytes, and just stream it down to one interlocked operation. The next one, we use this, or maybe we thought about a single writer principle. So if a value have a single writer and we can separate the writers that they will write to their own stores, we can make it much, much simpler and much faster. Still, because the presenter was a bit lazy and wanted to reuse the previously existing packed interlocked average, we used packed interlocked average to make that happen. But again, we observe some penalty because of this one interlocked. And the last but not least example, so in our case, that was reader writer average 2. We noticed that actually there is a single writer principle that we can apply in here, because the value is written and updated by a single writer. So then we can just move to volatile write, and on the other hand, the volatile read, and then they will just combine together and provide us with this beautiful, beautiful performance. So these were the old steps, all the phases that we went through to play with the average and to see how it works and how can we make it efficient.
Yeah, it was a great comparison, like going from the scratch up to the volatile everywhere.
Yeah, I mean, hopefully that's not the reasoning that comes out of this presentation, that you should sprinkle volatile all over your code. And actually, .NET 5 is really, really picky about not introducing too many volatile reads and writes because of the ARM architecture. And there were several PRs that basically stopped or copied the field to a local variable to do not harm the performance on ARM architecture. Yeah, sorry for this for sidetracking, but yeah. So I hope that you have these low-level doubts. I mean, that mostly we should not care about this, and I do agree that mostly you should not care about this, and probably using volatile is not the solution for making your ASP.NET Core application faster. At the same time, this code is used on the like a framework BCL library level. If you want to write a bit of more complex code, or if you want to implement your own pipe reader or writer, do this kind of stuff that deals with threads, tasks, sometimes you need to use these tools. The last step that I would say is that it's important, or it's nice to understand these concepts, because having this, then you can learn so much more, from instance, from the runtime, .NET runtime repo. And if you revisit some task-related code or async-related code, you could observe either usage of interlocked or volatiles. So now we could say that it's maybe not important, but on the other hand, I mentioned that it's in the runtime repo. So maybe you would like to see some examples.
Yeah, sure.
How it is used. Okay, so let's move on. The very first one is actually quite interesting, and it's quite new, because it's related to .NET 5 and value task pooling. If you're not familiar with this topic, what .NET 5 does, it introduces a feature that enables you to toggle or to switch the cache for state machines or state machine boxes. So what it will do, if you enable it, it will ensure that value task returning methods deep down .NET will use this kind of pool to lower the number of allocations, lower the number of allocated bytes for async-related tasks. So how it works? And actually, it uses both volatile and interlocked. So first, it uses interlock compare exchange. That's an atomic if operation. So what it will do, it will try to write to the static cache log field value 1 if there was 0 in there. So the last parameter of this method, that's the comparison. And it returns what was in there. So if there was 0 in there, we are safe because we ensure that we are the only ones that swap the value, because the swap is made in an atomic fashion like we observed before with add. Then there is some kind of logic with dequeuing a box from a list from the cache. And then we use volatile write to write back the 0 to the cache log, for instance. So why do we do it? Just to ensure that once the cache log is seen as equal to 0, we know, because of the semantics behind volatile write, that all stuff that was above, so playing with the box and the cache, will be seen as well. And the same goes if we don't find the box, we still want to release the cache. The last line in this method, as you can see, if we failed to find the box, just allocate the new one.
A quick question. Can interlock be applied here where we have volatile write? For example, interlock.
Definitely, we could do that. But as I mentioned, volatile write is much more relaxed. So by using volatile write and just saying, put a 0 in there, if we have a 0 in there, all that was written above will be observed as well. We are just fine, and that's sufficient enough to A, make it a correct algorithm, and B, make it fast.
Okay, so using volatile here is a way of optimizing the concurrent approach even to be even faster.
Definitely. Another case related to the, that name is quite mouthful, manual reset value task source core of T. That should be added. So basically, if you are considering doing like a alloc free and writing I-value task sources in .NET, you can use this struct that's already like an implemented struct for you to use. And it has a few methods in there. One of the methods that we could take a look at is related to onCompleted. So what it does, it tries to register, or sorry, not tries, it registers a continuation that you would basically, the rest of the code that is underneath the await. That's the continuation, right? So what it does, it will take the continuation and try to store it. But it needs to store it in an atomic way, and it uses compare exchange. The reason for that is simple. On the other hand, because we have an asynchronous operation that needs to be awaited, this operation might be completed by a third party. And when it is completed, it will use the very same continuation field to properly signal who was first. So again, we have a single field. We use interlock compare exchange to atomically swap it. And whether the continuation is assigned first or the actual execution is completed, we have this single point of synchronization that we will ensure that we will run the continuation properly. the whole code of this struct is so much longer, and it includes one more piece related to interlock compare exchange. But again, think about it as we have a single field, we have the actual completion that is, continuation that is registered, and we have this thing that is run somewhere in there that will be completed, and they need to synchronize somehow in this single point. And the last but not least, and a snippet from an awesome library, async-x, built by Stephen Cleary. Actually, Stephen is one of the mentors of our Async Expert online course, and that's order by completion, a really simple extension method that provided with an IEnumerable of task will provide you a list that will be completed by the order of completion. And let's not spend so much time on semantics and playing with it inside of this method body. But as you can see in here, again, we use the interlocked increment to bump up the index that should be used to set a completed task, let's say it this way. So we have multiple tasks that are run, but again, we have a single synchronization point, last index, that will provide us with the index that the value should be stored at. I hope it does make sense, so that we have, again, multiple agents, multiple running things that need this one single synchronization point to properly store an item in an array.
So for example, I can start 10 requests and order their completion. For example, I can ask for 10 websites, like their body, and in the response, I will have the list, which is ordered by from the fastest to the slowest, for example.
Yeah.
And this interlocked is used to separate, like to select the index for specific request. Like this is the synchronization point for the whole logic under the hood.
That's the thing. Yeah, that's a very good description of it. So again, a single synchronization point and usage of the atomic operation.
Nice.
So yeah, as you can see in here, you know that hopefully by this moment, you know that here in Dotnetos we really love low-level stuff. At the same time, our assumption is that it's vital to understand the basics of any approach if you want to truly master it. So going a step back, understanding the basics, and then building on top of it. And at the same time, we want to share the knowledge about modern async-friendly programming in .NET, or async-aware or async-ready programming in .NET, meaning using async-await and all the stuff related to that, task cancellation tokens, etc. And to answer these needs and to answer these questions, we created this Async Expert online course. And Łukasz, maybe you will say a few words about it.
Yeah, as Szymon mentioned before, we have an online course which is dedicated to asynchronous programming in .NET, where we cover a deep internals of how async works under the hood, how you can use it to perform your application, for example, much faster. We also cover things like concurrency, data structures. If you enjoy the interlock or volatile, we have it in our course. The course is based on the 10 weeks, so we have 10 modules, and you can participate in each module, for example, week after a week. The course is created by 3 of us, so it has 3 authors, Szymon, me, and Konrad Kulet. Each of us has created the materials, reviewed them, record them. Except us, we have 3 mentors, Mark Graver from Stack Overflow, Daniel Malbach from Particular Software, and Stephen Cleary, who is the author of the quite famous book called Concurrency in C# Cookbook. A lot of details about the course is available on the async-expert.pl and async-expert.com websites. However, since we are engineering, let's speak about numbers. Currently, we have almost 400 attendees, like the students who have participated in the course. The course has more than 900 slides. We have more than 28 hours of great video from 3 of us. We prepared the course in 2 language version. If you are brave enough, or if you are from Poland, you can take the Polish version. However, you can also enjoy the English version. And that's all. Szymon, would you like to tell us something more about the course?
Yeah, definitely. Beside the numbers provided in here, we provide guidance using our community or discussion groups that you can basically ask anything and that will be answered. On top of that, we will have 3 live sessions with our mentors. So you can either attend the session or ask a question before the session. The sessions will be recorded and added on top of the mentioned 28 hours of, or 28 plus hours of video. And on the pages, either Async Expert PL for Polish version or async-expert.com for English version, you will also find some feedback and opinions that our attendees shared with us. We are really happy and pleased with the feedback because it's really assuring that the value provided in the course does something that people expected and that they enjoyed when going through the Async Expert path. So the last but not least, the sale for this course is currently open. So we started it today. It will end on Friday, so September 25, 8 p.m. CES time, so Central European time. And if you want to join us, or we strongly encourage you to join us in this path, join us in this Async Expert online course. As I mentioned, a lot of detailed information is stored on the page. If you have any question related either to the course or Dotnetos in general, there is also a small pop-up that you can use to chat with us. We are also on social media, so feel free to ask any question related to the course. But as I mentioned, a lot of detailed information is in there on the page, and because that's second installment, maybe not an installment, but the second full run, we already gather some feedback that we are so happy to share with you. So if you have any questions related to this content of webinar, maybe not why average sucks or something like that, but something related to the implementation details, numbers, we have a few more minutes to answer them.
I think one of the questions is that we made an assumption that the sum that holds the average will be below the maximum value that int can hold, right? So if the value will be bigger, it won't work like that.
Yes, that's correct. I think that I mentioned it somewhere between the slides, but if I didn't, sorry. So yes, to pack values in a single long, we need to ensure that they are not bigger than this, the number you mentioned, because that's the highest integer number that you can store. An interesting thing to add, modern CPUs provide not only interlocked for long, but also interlocked for 16 bytes long values, but then without comparison. So you can compare, exchange them, for instance, widths, etc. And if you take a look into the runtime repo, there are multiple things related to how that would help to make the to make the switches of references fast and preserve or stop from happening the ABA problem. So yeah, but the point taken, definitely our assumption was that the sum and the count will be smaller than 2 to 32 power.
Okay, I see that we don't have any other questions, so I encourage you to ask them if you have.
Yeah, I can't see any of these. So I think that we'll be wrapping up. Again, thank you for joining us. And we strongly, if that was somewhat that makes you interested and presented some value for you, we strongly encourage you to take a look at the course pages that are filled with information. And as I mentioned, the doors are closing September 25, 8 p.m. Central European time. So thank you for being with us, and hopefully we will see each other soon. Take care and bye.
Yeah, thank you very much. And we hope this webinar was below or no, above the average, definitely above the average.
Definitely. That was the job. Take care. Bye.
Take care. Bye.